All right, everyone. Welcome to 311. This is the online edition, thanks to, unfortunately, the coronavirus. So we've all been kind of, schools have closed down and everything. So here we are, unfortunately. We're just going to try and continue and do the best that we can with what we got. And where we left off on was on the BJT. Specifically, we had done the base bias. And now we're going to go ahead and just modify the circuit a little bit. And we're going to switch this over to a voltage divider bias. So let me go ahead and move this intro here. All right, so the voltage divider bias looks like this. If you've noticed, we've gone ahead and kind of added a few things here. I'll put it in comparison over here. I have a little sketch over here of our base bias circuit. This is the one that we've been used to seeing. There's really only two resistors that were involved here. One in order to limit the current going into the base of the transistor, and then another one over here on the collector side. Now we've seen it in this form where we separated the base bias voltage and the collector bias voltage, but we've also done the circuit where they've shared the same voltage, and both of these are essentially identical. They're both the base bias version of the circuit. What we're doing over here with the voltage divider bias, however, is notice we've now added a second resistor to the base. In fact, from VCC through R1 and then through R2, what we've done is created a voltage divider right here. As well as we've added, and this is a little hard to see right here, this is the emitter resistor. We've also added an extra resistor. So we've added two resistors to our original circuit. Now there's some advantages to this circuit. There's some reasons we would use it, and the most common transistor circuit you're going to find in the field is this one. And there's a good reason for that. That's because when we bias the base of this transistor with a voltage divider, what we can actually do is cancel out the changes of beta, right? So if you remember the collector current is proportional to the amount of base current that we have entering the transistor via that term beta, the intrinsic gain, the intrinsic current gain of that transistor. And of course you saw that with the linear model. Okay. However, in practice, beta is not a fixed value that we can rely on. So if you look over here, if we just draw a characteristic curve, this would be IC along this the y-axis, and VCE across the x-axis here. And for different base currents, you'll actually arrive at different betas in practice. So with a real transistor, you're going to get beta, sometimes might be 80, other times it might be 120, and all in between. This is to be expected. These are real components. This is how they behave. And we can expect that beta will actually change based off of the temperature, the humidity, transistor replacement. So even if I made 100 transistors in the same process, in the same factory, using the same materials, each one of them will have beta that changes a little bit. And also based off of how you use the component, you can also expect beta to change. So the whole reason for using this circuit is because we can actually cancel out some of these effects of a changing beta. So I do have an example where I will show that. where when we change beta for a given transistor and we keep all the components the same, you'll actually end up getting similar values. So this is fairly tolerant to changes in beta. It's not perfect, but it's a lot better than the base bias version. Okay, so just to kind of set our bearings, we have an R1, R2. I'm calling these R1 and R2 because for the voltage divider, we've always used R1 and R2. And we have a collector resistor since it's attached to the collector, and we got an emitter resistor that's attached to the emitter. And still all of the things we talked about previously, like the emitter current here is equal to the base current, so the base current that's entering plus the collector current, right? Kirchhoff's current law is still being held. Okay, so we do have a few different ways to solve this circuit. There's a couple of different techniques. I would say there's about 3 popular different ways to solve this. I'll go ahead and break that up. And I'll say solutions to the BJT voltage divider bias circuit. Okay, so a couple different ways to solve this. The first one is actually the method we're going to learn here. We're going to go ahead and Thevenize. Actually, let me go ahead and say the Thevenin solution so we can actually apply Thevenin's theorem and we can reduce the circuit into something very easy that we can solve. That's going to be the first technique that we learn. The second is going to be an approximation technique. And the third is actually a combination of nodal analysis and some basic rules. The nodal analysis and basic rules technique to solve the voltage divider bias is actually a little bit of a... It's not terribly difficult, but it is a little more lengthy. I find that the Thevenin solution works pretty well, and the approximation technique is incredibly easy. So we're going to learn these two, and I'm going to not even worry about this one. Okay, so we're going to focus on these two different solutions. And in fact, in this module for today, we're just going to look at doing the Thevenin solution. And then later, I'll go ahead and teach the approximation technique. Okay, so let me go back to my notes. Okay, so here is that circuit. Now, if you notice, I've actually redrawn this. Let me go ahead and put both of these up there so I can show you what I've done here. All I've done is actually redrawn this circuit. Instead of having this common VCC, I'm still calling it VCC. These are still the same exact values. All I'm doing is switching it over to this side. in order to break the circuit up into these two sections, okay? So I've gone ahead and turned this into a voltage divider right here. Clearly we have a V in, which is VCC, and then that voltage gets reduced to whatever we get here, right? By the ratio of R1 and R2. And I've gone ahead and drawn this ground to signify both of these are connected to each other. But this circuit hasn't changed, right? It's the exact same as this. The transistor's in the same place. RC is still at the top. RE is still at the bottom. All we've done is redrawn this so that I can make it really clear how we can Thevenize the circuit in order to simplify it. Okay, now if you remember from 211, when you do a Thevenin equivalent circuit, what you're really doing is just taking any complicated linear circuit comprised of any number of voltage sources and any number of resistors, and you're turning it into this form. And that's what Thevenin's theorem allows us to do. Pretty simple technique, and we just go ahead and turn this, and I've gone ahead and kind of made a dotted box to show you what the circuit is that we're going to turn into a Thevenin equivalent. And if you remember, a Thevenin equivalent circuit consists of a Thevenin voltage, so we will be calculating a new voltage source here, and we're going to be calculating a Thevenin resistance here. And then also remember, we always have to Thevenize a circuit from 2 points, right? So the perspective is that this circuit will behave in every which shape, way, and form to this circuit from points A and B. Okay, so all we got to do is turn this into this, right? Okay, and what that's going to allow us to do is, if we find a Thevenin equivalent circuit for this voltage divider portion over here, then when we derive the Thevenin equivalent and we substitute this circuit, the Thevenin equivalent, in place of our voltage divider bias over here, look what we get. We get our same circuit back, right? We get almost the base bias version of the circuit back. Okay, the only thing that's different than what we've already been solving in previous classes is that we have this emitter resistor down here. Okay, so that's our motivation for doing this. We take this, we turn it into our Thevenin, we plug our Thevenin back into our original circuit, and we get this, right? Where we have a Thevenin voltage that is being applied to this base resistance, or which is RTH that we solve for. And then we can solve for our base current, and we can go through that DC analysis steps that we've done in previous classes. Okay, so enough talking about the motivation and what we're doing. Let's go ahead and just figure out how to do this. Okay, so what we need to do is find the Thevenin voltage and Thevenin resistance for this circuit, right? Now, remember what it is, or what the Thevenin voltage is defined as. VTH, or the Thevenin voltage, is simply the voltage between points A and B, right? So, if we find the voltage between A and B, we have our Thevenin voltage. That's all we got to find, this voltage right there between A and B. Well, that's really incredibly easy to do, because if you notice, all that is a voltage divider, right? Sorry, I know I'm moving this around a a little more than I had planned to. If you notice, all we have is VCC applied to R1 and R2. So if you think about the voltage divider equation, I'll go ahead and draw this over here. We have a Vin, we have an R1, we have an R2, and we have a V out, right? This is our voltage divider. So V out is going to be some value less than V in, right? And the equation that we get is V out is equal to V in times R2 divided by R1 plus R2. Okay, and you can figure this equation out from your basic rules. So I'm not going to go over how to do that. Hopefully everyone remembers how to do that. This is just an incredibly useful simple circuit that pops up left and right. Anytime we want a voltage that's less than what our input is, we can go ahead and use a voltage divider. Okay, and as you can see, the voltage at A is VCC times R2 divided by R1 plus R2. Okay, that gives us the voltage at that point. Well, what's cool is our B terminal is referenced to ground. So this is 0 volts right here. And this essentially is V out of our voltage divider. So no surprise, our Thevenin voltage is just VCC times R2 divided by R1 plus R2, just our voltage divider. Okay, so that gets us to figuring out the Thevenin voltage. The last thing we need to do is figure out the Thevenin resistance. And so if you remember, to find the Thevenin resistance, all we got to do is short out VCC, or short out all of our voltage sources, I should say, in general. But in this case, we only have one voltage source. So you short out that voltage source, and you find the resistance between A and B. That's all we have to do to find the Thevenin resistance. Well, if you notice, once we short out the voltage source, it now places R1 in parallel with R2, like this, between points A and B. Okay, so now our Thevenin resistance is actually just R1 in parallel with R2. And R1 in parallel with R2 is just equal to R1 times R2 divided by R1 plus R2. Okay, so this circuit for a voltage divider bias pretty much never changes. Well, I should say it never does change. So these two solutions are always valid for a voltage divider bias, right? If we're going to apply the Thevenin technique of solving it. Okay, so that was kind of a bit of a refresher on Thevenin equivalent circuits, and these are our two equations that we end up with. Okay, and now for this circuit, we know how to find VTH, we know how to find RTH, RC, and RE stay the same. All right, now keep in mind the goal here is we want to find out our operating point. I don't know why this says conditions. Operating point or operating parameters. But regardless, we're trying to find the base current, the collector current, the voltage between the collector and emitter, and I guess also the emitter current, right? Okay. So we're trying to find the base current. Once we find the base current, then we can figure out the collector current. Once we figure out the collector current, we can figure out VCE. So obviously we need to go ahead and step through our DC analysis steps. Okay, so let's go ahead and let's first figure out how to find IB. Well, we end up doing that with a Kirchhoff's voltage law expression or KVL expression, and simply put, we have VTH minus the voltage drop across the Thevenin resistance over here. Now the voltage drop across this is equal to RTH times IB, right? That's just Ohm's law over here. Okay, so the voltage drop across RTH is just the current times the resistance. Okay, now that's not the only voltage drop involved in this. We also have a voltage drop from the base to the emitter. We always keep that at a fixed value of 0.7. Remember, over here you have a PN junction, so we have a diode that's been created between the base and the emitter. And so that diode, since it's constructed in silicon, we can just take that to be a fixed value of 0.7 volts. And we have one more voltage drop involved, okay? Now this is new, right? We didn't have this emitter resistance in our original base bias circuit, right? That base bias transistor circuit that we learned how to solve before all of this happened, right? So we need to also include the voltage drop across RE. Well, no problem. The voltage across RE is nothing more than the emitter current times the emitter resistance. And we're all the way back. This is one entire KVL loop, right? The sum of all voltage drops in any closed loop should be equal to 0, so this should be equal to 0. Okay, now we could solve this. However, we're going to run into one problem, which is to figure out the base current, right? Remember the goal here, we want to figure out the base current. That's our first step in this process. However, we don't have the emitter current, right? The emitter current is a function of the collector current. And to find the collector current, we need to figure out IB. But it looks like from this equation, in order to figure out IB, you would need to find IE. But to get IE, we need IC. And to get IC, we need... okay, we got a chicken and egg problem here, right? This IE is kind of throwing a little bit of a monkey wrench into this problem. Because to find it, we would need to already know IB. So we need to rewrite IE in some other form that we can go ahead and get rid of. Now over here, I've kind of gone back to this simplified base bias circuit with no emitter resistance here, just to demonstrate how we can rewrite this emitter current. Okay, we know that IC is equal to beta times IB, right? The collector current is just equal to the intrinsic gain of the transistor times the base current. And we know that by Kirchhoff's current law, IE, the emitter current, should be equal to the base current plus the collector current, right? Just KCL over here. Now, if I rewrite this, IB plus IC, I can say that IB plus beta times IB, right? Because IC is equal to beta times IB. So I can substitute this in over here, and I get IB plus beta times IB, right? Just a straightforward substitution with the definition of what the collector current is equal to. So we have we have KCL here, and up here we just have the collector current is equal to beta times IB by definition. So we can get to this substitution pretty easy. Now, check out if I just pull out the IB, right? So if I pull out the IB, this is just IB times 1 plus beta. So I end up getting this reduction. So we can say that IE is equal to beta plus 1 times IB. And then I can take that and substitute it into my original KVL expression that we're using to find the base current, and check out what we get. The Thevenin voltage minus IB times RTH, that didn't change, minus that 0.7 volts, the voltage between the base and the emitter, that stays the same, minus beta plus 1 IB. This is now being substituted for the emitter current, and that times the emitter resistance for Ohm's law gives us the voltage across the emitter resistance. All of that equal to 0. And now what we have is an equation that we can solve. We know what VTH is because we already would have solved for that. We're trying to find IB. We would have already solved and known the Thevenin resistance. This would just be 0.7 volts. We should know what beta is for the transistor. If not, we'll just take 100. Plus 1 times, again, we're trying to find the base current, times the emitter resistance, which we would have already had that value. All of that equal to 0. So we can go ahead and just rewrite this and solve for IB. Okay. So let's go ahead, do some algebra and solve for IB, and here's my cheat. I just skipped ahead, and here's what it ends up being. IB is equal to the Thevenin voltage minus that 0.7 volt drop between the base and the emitter divided by the Thevenin resistance plus beta plus 1 times the emitter resistance. Okay. So we've actually found beta now. We know what that is. IC and IE are pretty easy to solve for at this point. IC will just be equal to beta times IB, and IE will be equal to, well, we already showed how to solve for this, beta plus 1 times IB. Okay, so that gets us IB, that gets us IC. Now, the last thing we do need to solve for is VCE, the voltage between the collector and the emitter. Now, we're going to go ahead and just write another KVL loop. Okay, so over here, all we're doing is expressing a Kirchhoff's voltage law loop from VCC across the voltage drop from the collector resistor, across the voltage drop VCE, and across the voltage drop across the emitter resistance. Okay, so we start at VCE, end up at 0 volts. Okay, so obviously to find VCE, we're going to do VCE is equal to VCC minus the voltage drop across this, and minus the voltage drop across this, and that gets us our VCE. All right, let's check it out. So the voltage between the collector and the emitter is equal to the collector voltage, I should just say VCC, minus, and now we need to go ahead and say, well, actually, let's look at this top one first. Sorry, I shouldn't have jumped ahead. This is a reduction. Start here. VCC minus the voltage drop across the collector resistor, right? It's just current times the resistance, just Ohm's law there, minus the collector emitter voltage, which is what we're trying to find, minus the voltage drop across the emitter resistance, which again is just Ohm's law, IE times RE. And then set that whole thing equal to 0. Now, we can go ahead and make a little assumption over here that makes life a lot easier. IC is approximately equal to IE. All right, why am I saying that? Well, check it out. IB is in microamps, right? That's tiny, very small current. IC, on the other hand, is in terms of milliamps. Okay, it's off by a factor of 1,000. That's a huge difference between these two. Sorry, I should have said off by a factor of 100. Okay, so off by a factor of 100. That's a big difference between these two. So what I'm saying is that we can consider this to be negligible. Okay, so what I'm saying is that the contribution of the base current to the emitter current is very small. It's almost negligible, right? Because IE is equal to IB plus IC. This is true. It's just KCL, right? So what I'm saying is this being microamps and this being milliamps means we can go ahead and in this specific case not worry about it, right? We can just go ahead and say that the collector current is approximately equal to the emitter current. And if we do that, then over here I can go ahead and say that IE is equal to IC. And then once I do that, I can go ahead and pull both of those terms out. And then, of course, we're trying to solve for VCE, so I'm going to throw VCE to the other side of that equal sign. So what we end up with is VCE is equal to VCC minus IC times RC plus RE. Now, over here I have a little bit of a lecture note to myself, which is normally I'd be asking the class now, why is it that I can go ahead and make this assumption here, but not when we were solving for IB previously? Now, we can make this assumption over here, the IC approximately equal to IE. We can do that because when we're calculating for VCE, the contribution of IB to this expression is very negligible, microamps to milliamps. However, when you're solving for IB, the contribution of IB, well, it would make that it would change the value a lot. So we can't ignore IE, or I should say, we can't ignore the difference between IC and IE when you're solving for IB. Okay, so we can't make that approximation that We can't do that when we're solving for the base current. But we can when we're solving for the collector emitter voltage. Okay? Okay. So enough of looking at symbols. Let's go ahead and solve one of these. I'm sure at this point, hopefully, when we step through a real solution, a real calculation here, hopefully this makes sense. Okay, so here's our circuit. 20 volts applied, 50K for R1, 10K for R2. This is our voltage divider bias for this transistor circuit. We have a collector resistance equal to 3K. We have an emitter resistance equal to 1K. And we got a beta that's equal to about 200. Let's just go with 200 for this problem. Okay, now to solve this, we're going to go ahead and use that Thevenin technique. So what we need to do is turn this circuit into this circuit. Notice everything stays the same, 20 volts, 3K, 1K, our transistors in the same place. But here we got VTH, and here we have RTH. Okay, so we need to figure out the Thevenin voltage and the Thevenin resistance. We find those two. We now have a circuit that we can solve. So let's go ahead and step through that. VTH here is going to be equal to, well, it's just our voltage divider equation, right? So 20 volts times 10K divided by 10K plus 50K, we end up with 3.3 volts. That's our VTH. Okay, so we plug in 3.33 volts over here. That's how we get that value. All right, next up, we need to figure out RTH. Well, remember that when we Thevenize it and we short out that voltage source and we find the resistance between the terminals A and B, it ends up being that R1 is just in parallel with R2. So we got 10K times 50K divided by 10K plus 50K. Okay, that's going to end up giving us 8.33K ohms. So we go ahead and plug that in. All right. Now we're going to go ahead and solve this circuit. Okay, so here at this point, the rest of this is we're assuming linear mode, and we're going to go ahead and just solve for our operating point. We're trying to find IB, we're trying to find IC, and we're trying to find VCE. Okay. That's what we're interested in finding, our operating point. Okay, so now we're going to only be working with this version of the circuit. So let's go ahead and solve for IB. Now, I'm using those equations that I derived earlier for IB, right? The Thevenin voltage minus VBE, which is 0.7 volts, divided by the Thevenin resistance plus beta plus 1 RE. Just go back in the video or go back in your notes. You'll see how we arrived at this for our base current. So we go ahead, plug in all our values. Let me get this all on one page here. And so we get 3.33 volts minus 0.7 volts, all divided by 8.33K, plus, now here's where we plug in our beta. Our beta is 200. That's intrinsic to the transistor. 200 plus 1 times 1K, okay? And we arrive at a base current of 12.56 microamps. All right, so that's our base current. So over here we got 12.56 microamps entering the base of the transistor, following this path that I keep on outlining with my pen. All right. Next up, we need to figure out IC. Well, remember, IC is equal to beta times IB. It's just the gain of the transistor times our base current. We already figured out our base current was 12.56 microamps. So 12.56 microamps times 200 gives us 2.513 milliamps. Okay, so that gives us IC. We figured out IC. 2.513 milliamps. Okay, next up we need to figure out VCE. I already figured out this equation earlier in the notes. So VCE is equal to VCC minus IC times the collector resistance plus the emitter resistance, right? Okay, so VCC minus IC times the quantity RC plus RE. 20 volts here. IC we already solved, 2.513. We know that RC is equal to 3K and RE is equal to 1K. Solve that out, you're going to get 9.948 volts for the voltage between the collector and emitter. Okay, this is our Q point, right? So we got 9.948 volts. Okay, so that's our Q point. Now, if you notice, when I solved this, I made the assumption that this was in the linear mode. Now, realistically, you would, if you got that IB was less than 0, then you know it couldn't possibly be in linear, or sorry, if it was less than 0, blah, 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 blah. Screw that up. Okay. If IB ends up being less than 0 amps, we know it's in cutoff, right? But we didn't. We got a positive value, 12.56 microamps. Okay, so we know it's not in cutoff, right? And so then we went ahead and said, well, now we need to figure out VCE to figure out if we're in linear or in saturation. Well, to figure out VCE, we had to find IC. We found IC equal to 2.5 milliamps. Then we could solve for VCE. VCE ended up being greater than 0.2 volts. Since it's greater than 0.2 volts, our initial assumption of linear mode was correct. And so this whole solution is valid. Okay, so I left out those steps from this solution. And now we need to go ahead and figure out the load line. We figured out our operating point. Let's move on to the load line. Load line, we're just going to be plotting the collector current at saturation. We mark that along the y-axis. Along the x-axis, we mark VCE at cutoff. Okay, so let's go ahead and jump back to this circuit. Take a look over here. All right, let's look at cutoff. In cutoff, this would be behaving like an open switch. Well, if it's an open switch, we have zero current flowing through it. If we have zero current flowing through this, we have zero current flowing through it. We have zero voltage drop across all of these. So if we have zero voltage drop across all of that, then VCE would be equal to 20 volts. Well, there we go. Our VCE is 20 volts at cutoff. Cool. Okay, let's figure out the point along the y-axis for our collector current. Now for that, we're just going to figure out what the collector current is at saturation. Now, when we say at saturation, this is assuming VCE is equal to 0 volts, not 0.2 volts. Don't get confused with that. This is just 0 volts between the collector and emitter over here. So we're assuming 0 volts here. Okay, so essentially as saturated as this transistor could possibly ever get, behaving like a perfect or ideal closed switch. So if that's the case, what's the collector current? What would be the max current that could flow through between the 20 volts to ground if we had a 0 volt drop between the collector and emitter? Well, it's just going to be 20 volts divided by 3K plus 1K, right? Resistance in series adds 3 plus 1K is 4K, and Ohm's law gives us the current. IC is equal to 20 volts divided by 4K. Well, it's exactly what we did here, okay? So we go ahead and figure out what this y-intercept is over here. Our collector current at saturation, assuming 0 volts between VCE, gives us 20 volts divided by 4K, which is 5 milliamps, okay? So this load line goes ahead and defines all possible operating points that this transistor circuit could be in, given different inputs. Okay, now we haven't given this different inputs, it's just currently being biased to one value, which is why our Q point, we already found it, right? We found that IC was equal to 2.513. Well, that's about halfway between 0 and 5 milliamps, so I went ahead and marked that here. And we found that VCE was 9.948 volts. Well, it's got to be between 0 and 20 volts. Well, that's right here. Okay, so we found that our Q point is actually right in the middle of that load line. And that's actually a pretty good thing. Once we get to amplifiers, we're going to see that that is a very nice thing to have. Our Q point sitting right in the center of that load line. Okay, so that's essentially our solution. That's how we approach a problem like this. Like I said, this is one technique of several. We're only going to learn the Thevenin and approximation solution. Those two, I think, is more than enough for us in this class. So at the beginning of this lecture, I did mention that the whole point of this circuit is to compensate for changes in beta. In other words, what happens if beta is 100? What happens if beta is 200? Well, in the base bias circuit, this Q point would be all over the place with beta changing on us. And that's a tough situation to be in, because like I said, beta is going to change based off of temperature, humidity, different transistors in the same production line. I mean, you could look at the thing and beta is going to change on you. So having a circuit that can compensate for varying or changing betas is pretty useful for us. So what I went ahead and did was I went through this same solution, all the steps that we already did. I did it 2 other times with drastically different betas to see how our operating point changes. Okay, so remember, we solved this assuming a beta of 200, but if I had solved it with a beta of 100, so say I took out that transistor from the circuit, I put in another transistor, and that transistor, instead of having a beta of 200, it ended up having a 100 beta. Well, I end up getting that IC is equal to 2.4 and VCE is equal to 10.3. Now, 10.38 sounds different than 9.948. Totally agree with you on that. However, look at it from the perspective of the load line. As far as this transistor circuit is concerned, it could be all the way over here, or it could be all the way over here at cutoff, right? All the way from cutoff to saturation. So if beta had somehow changed because the temperature changed in the room from 200 to 100, right? It dropped in half. That's quite a big change in beta. Then VCE would have only increased by less than 1 volt, less than half a volt. We're talking about shifting right here. Like, I can't even draw that. That's so close to it, right? As far as this line, it could have been all the way over at 20 volts. But it's still really close to that Q point, right? And IC, of course, it just dropped down just a bit. It went from 2.5 to 2.4 milliamps. Again, that's no big deal. It's right about here on this load line. It really didn't change all that much. Now again, if I step through the whole process, assuming that our beta all of a sudden jumped up from 200 to 300, which again, that's a huge change. Well, I already solved it for you. IC would have gone from 2.513 to 2.551. We're talking 0.05 milliamps. That's 50 microamps. That's nothing. Actually, it's 40 microamps. That's a tiny change. The Q point just shifted barely right there. Like, I can't even draw it. VCE went from 9.948 to 9.796. Okay, again, it dropped down just a little bit. So, as you can kind of see, that by just adding 2 resistors to this circuit, we didn't increase the complexity that much. All we did going from our previous circuit to this one, we added 2 resistors, the emitter resistor and the R2, right? We changed this to a voltage divider. So by just adding those 2 resistors in there, we essentially made a circuit that doesn't care if beta fluctuates. And that's why you're going to find that this circuit ends up being the most popular BJT circuit in every single circuit constructed, right? If you're using a transistor, if you're using a BJT, if you're going to make an amplifier, you're probably going to see this, right? And that's the reason why, because this is very much doesn't care about changes to beta. Okay, so I'm going to leave this here. This is actually my first online lecture that I'm attempting to do. I probably didn't get this perfect, and I will be working on this to try and get my my YouTuber skills up. All right, so please take care of yourself, wash those hands, and I will see you next time. Feel free, I will be having Zoom sessions for my, Zoom for my office hours. So please feel free to drop me an email if you want a different time for my office hours. I'm happy to pull up Zoom, do some video conferencing, help you guys out however you need. And just stick with us. Just bear through it. We'll all get through this. Yeah, and we'll make it out of this. All right. Well, take care, guys. I'll catch you later.